experiment of the semester, experiment 10. This is an acid-base titration experiment. We've discussed this briefly in class in lecture 16, so please go back and revisit lecture 16 for some concepts. As well, it would be helpful if you read section 15.3 to 15.5 and 15.8 to 15.9. That will allow you to be better prepared for this lab. So the lab will be held immediately after Thanksgiving on Monday the 28th and Tuesday the 29th, depending on your lab sections. Let's go over a few things that we've already kind of discussed in lecture. We mentioned in lecture that titration is basically a method that is used to precisely and accurately determine the volume of a standard solution required to react with a reagent of unknown concentration. Now you'll see in today's lab, or in this week's lab, in part A, we're trying to determine the concentration of the standard solution, whereas in part B, we're actually determining the concentration of an unknown reagent solution. And I'll explain what I mean by that when we cover each part in depth. I want to remind you that we have this concept called equivalence point in titration, and it's basically the point at which stoichiometrically equivalent quantities are brought together. So again, we're going to have to use stoichiometry, and what that really means is that we have to ultimately write out a balanced chemical reaction and use the coefficients to know how to convert from 1 mole of reactant or products to another mole of reactant and products. Equivalence point is also oftentimes known as the endpoint. So let's just dive right into each part of the experiment. You're going to be working in pairs this week. In part A, the goal of part A is to actually determine the true concentration and molarity of the standardized solution. So if you look into your lab manual, it says that you're actually preparing a standard sodium hydroxide solution. That sodium hydroxide solution we're referring to as approximately 0.5 molar base. So it's not exactly 0.5 molar, it's around 0.5 molar, but we're going to be using titration to identify exactly what that concentration is. So when you prepare your sodium hydroxide standard solution, your instructor should demonstrate on how to use a burette. You have to first make sure you properly clean your burette. Again, ask your instructor how to do that. You're going to fill your burette and follow the instructions carefully with the standard sodium hydroxide solution that you've prepared. And again, we're referring to this as approximately 0.5 molar base solution. In your flask, you're going to measure an exact amount using an automatic dispenser of 1 molar HCl. So you know the exact amount in milliliters and the exact concentration of HCl. So if we use an example similar to problem 12.31 in lecture 16, you'll see that we've actually done this before in class. So you're going to again fill the burette with your standard sodium hydroxide solution, and you're going to fill a flask along with phenolphthalein indicator. You're going to put a few drops in there. Make sure you record all your observations, initial observations, final observations, how many drops of indicator you use, how many milliliters, your initial burette reading, final burette reading. These are all very important parameters that you're going to be graded on in your lab notebook. We have a known concentration of acid in here with a known amount of acid because we're using automatic dispensers. And these automatic dispensers are set to precisely the volume that we want to use. After titration, you've read your initial burette reading. Now you're at a final burette reading. So now you can calculate the volume of base used to neutralize your acid. So this is what titration is. In lab, you should observe a very faint pink color. But the key here is that this pink color has to persist for a few seconds. So make sure, again, you follow your instructions in your lab manual because it tells you how many seconds this color needs to persist. Really, once it changed to a faint pink, you're good to go. And you're going to repeat this procedure 3 times and take the average of these measurements. So let's go through a sample calculation together of what you'll actually have to do in lab. So in steps 1 through 11, you're preparing your standard sodium hydroxide solution. You don't know its exact concentration. You're performing your titration experiment. You're neutralizing your acid because it reached its equivalence point, its end point, and we know that because of this color change. And now in step 12, you're actually asked to calculate the concentration of your sodium hydroxide solution. So let's, again, this is a sample calculation. Obviously my numbers are much different than what you'll get in lab, but you should get an idea. So here we're being asked, what is the molarity of a sodium hydroxide solution if 48 milliliters neutralizes 35.0 milliliters of 0.144 molar sodium hydroxide? Again, we've done this several times in lecture and on your homework. If you want to go back specifically, this is a useful problem, or just use the problem that I'm giving you here. So let's go ahead and first write a balanced chemical equation. So we have sodium hydroxide solution. It reacts with hydrochloric acid to produce sodium chloride and water. And remember, this is a neutralization reaction, which is why we get a salt and a water. The problem tells us we use 48.0 mils of sodium hydroxide to neutralize 35.0 mils of hydrochloric acid, and the concentration of hydrochloric acid is 0.144 molar. We're asked to find the molarity of sodium hydroxide, the true molarity, which is exactly what the goal is for part A in your lab. So remember, molarity is moles over volume. You guys should all be experts at this point. So we know we can find moles of HCl, and once we find moles of HCl, we can use stoichiometry to find moles of sodium hydroxide, and then we use this equation to find the molarity of sodium hydroxide, because again, that's what the problem is asking us for. So let's go ahead and calculate moles of HCl. We can do so because molarity, if we rearrange this equation, moles is actually equal to the molarity times volume. So plugging in our values here, we have 0.144, capital M really stands for moles over liters, times 50 liters, so I converted the liters in my head. These cancel out and the following moles of HCl. Now we want to find moles of sodium hydroxide, because if we divide it by the volume in liters, we can get molarity of sodium hydroxide. So if we use stoichiometry, we want to convert moles of HCl to moles of sodium hydroxide, so now we're using the coefficients. Now this is a completely balanced chemical reaction, so all the coefficients happen to be 1 to 1 to 1 to 1. So that means per 1 mole of sodium hydroxide, we need 1 mole of HCl. And again, that's because the coefficients are all 1 here. These cancel out, and I get 0.00504 moles of sodium hydroxide. So that means the molarity of my sodium hydroxide standard solution is my moles divided by the volume, which is 0.0480 liters. So please make sure you actually do this conversion in lab. So the true molarity of the sodium hydroxide in this specific example is 0.105 molar NaOH. So that's part A. You're determining your true concentration of your sodium hydroxide standardized solution. And now, in part B, you're going to use that information to determine the concentration of the vinegar solution, so the acetic acid solution. So in step 1 and 2, you're really just doing a repeat of what we did in part A, by you're filling, now it's a known concentration of your sodium hydroxide solution, because now you actually calculated it in step 12 of part A. In your flask, you're putting an exact amount of milliliters of acetic acid. We call it vinegar. You're adding to this phenolphthalein indicator, and you're going to titrate. Again, you have to read your initial burette reading, and then once you get a color change, a faint pink that stabilizes for a few seconds, you want to get your final burette reading, and your final or initial minus final gives you the actual volume used to titrate acetic acid. So again, let's do an example together because you are graded on whether or not you can actually calculate the concentration of your vinegar in part B and your concentration of your standardized sodium hydroxide solution in part A. So an example here, we're saying 47.5 milliliters of 0.5 sodium hydroxide is required to neutralize 20 mils of acetic acid solution. What is the concentration of acetic acid solution? This is very similar to what you're doing in lab, except obviously different values. So again, we always start off by writing a balanced chemical equation. So we have sodium hydroxide reacting with acetic acid to give us water. So titrations are all neutralization reactions, and here it tells us we're neutralizing us to form water. And with acetate salts, the way we write it is the following, and we'll go over that heavily in chapter 15 when we cover acids and bases. Now we want to make sure our equation's balanced. It's indeed balanced. So let's write down what's given. We're given 0.5 molar sodium hydroxide, a volume of 47.5 milliliters, and we're trying to figure out what the concentration is of acetic acid from this. So again, remember, molarity is moles over volume. We can rearrange this to solve for moles, which is molarity times volume. So if we've solved for moles of sodium hydroxide, we can then use stoichiometry to find moles of acetic acid. Once we find moles of acetic acid, we can use this equation to find the molarity of the acetic acid solution. So let's go ahead and dive right into this. Moles of sodium hydroxide is equal to the molarity of sodium hydroxide times its volume. Now remember, molarity is moles over liters, so you have to make sure your units are proper. So we go ahead and do this math out. So now we found moles of sodium hydroxide. Now we want to find moles of acetic acid. So we use stoichiometry, and if we have moles of sodium hydroxide, we can multiply this by the stoichiometric ratios, which say you have 1 mole of acetic acid per 1 mole of sodium hydroxide, because all my coefficients are 1 to 1 to 1. These cancel out, and I get the same exact value for acetic acid, for moles of acetic acid. So now that I have moles of acetic acid, I can go ahead and plug it into my molarity concentration to find the concentration of acetic acid. So capital M is equal to my moles divided by the volume. In this case, it's 0.20020 liters, and I will get a molarity of 1.19 molar acetic acid solution. So now I've determined the concentration of my acid. Again, that is the goal in part B of this experiment. Part C is a really fun part of the experiment because you get to experience or investigate what the effect of a strong acid has on a buffer versus an unbuffered solution. So some of you might have heard this term buffer before, but if you haven't, a buffer solution is basically any solution that resists major changes in pH. And the way it does that, it contains an acid to neutralize any OH ions that you add, so right away it neutralizes it, or it contains a base that neutralizes any hydrogen ions that could be added. So hydrogen ions are added from an acid, OH ions are added if you add a base. Our body is one of the most efficient and productive buffer systems there are. So we're always, all of this neutralization is constantly happening in our body. So to give you an example, this is an unbuffered solution. So this is actually step 1 of part C. You have an unbuffered solution. You're adding a universal indicator. So please pay attention. You have 2 different types of indicators that you're using in lab. The universal indicator is what you're using in part C. You're not doing any pH measurements in lab this week, but however, you're using the color change to determine the effect of a buffer versus an unbuffered solution. So for this specific example, if you have an unbuffered solution and you add an acid, which supplies, we call it hydrogen ions or hydronium ions, you're going to see a change in pH, and you can't read this here, but that change of pH is 4.0. If you add a base, so for example, if you add sodium hydroxide, that change of pH is going to go up, right? Because remember we talked about acids being less than 7, bases being greater. Here, this solution does not resist major changes to pH. In pH. And again, because we're seeing pH actually change. If you had a buffer solution, your pH should not change. What you're going to see in lab is a color change. It might not be red and blue. I actually don't remember what it should be in lab, but pay attention to your colors. Make observations before addition of acid and after addition of acid. And in lab, you're only looking at effect of a strong acid. You're not looking at base this time around. So now let's look if you had a buffer solution. So again, it's around neutral pH. Your buffer solution, if you add an acid to it, so in lab, you're actually adding HCl. That, if you're measuring the pH, that pH will be very, very similar. And if you add a base, so let's just say if we added sodium hydroxide, that pH will also be very similar. So here we see the buffer solution in fact resisted major changes in pH. In lab, what you're going to be doing is looking at, again, colors. So you're going to see that the unbuffered solution, when you add the universal indicator and then you add HCl, you're going to see an instant color change right away. You have to record number of drops of HCl to actually see that color change. Now with your buffered solution, you're going to add HCl and you're going to keep adding drops until this color matches the color of your unbuffered solution. So I want you guys to think, would that number of drops be more or equal to the number of drops required here? I hope you've come to the conclusion that the number of drops is going to be significantly more because a buffer solution will resist major changes of deep pH. That doesn't mean that it'll never change, it just means that you're going to have to dump a lot of acid to actually see a pH change, which in lab this week we're seeing it by a color change. The buffer solution that you're going to be preparing in lab is using sodium bicarbonate, and you're asked in lab in step 2, in your sodium bicarbonate solution, which is mostly water because it's only 0.1 molar sodium bicarbonate, you're going to be blowing CO2 gas. Now, when you blow CO2 gas, you actually end up forming carbonic acid, which is a weak acid. And again, we're going to learn about this in chapter 15, but please make sure you read those sections that I mentioned early in pre-lab. And you're also forming water, but this is also in equilibrium with a hydronium ion, or if you just want to refer to them as hydrogen ions, you can refer to them as hydrogen ions, and a bicarbonate ion. And this bicarbonate ion is a weak base. So this is the most effective buffer system that you have. So this portion is what you're preparing in lab, and that's why it resists major changes in pH. So a few experimental logistics. You're working in pairs this week because there's a lot of maneuvering with the titration and making sure that you don't surpass the equivalence point. So you want your, in part A and part B, that color change to be a very faint pink. If it's a dark pink, you kind of surpass that equivalence point, that end point, and you should really redo it, but leave it up to your lab instructor. As I mentioned over and over again, make sure you record all initial and final observations. It's very important to record your initial and final burette volume. Please read the instructions carefully because it tells you to refill your burette each time, because you really don't know how much of the standard sodium hydroxide solution you're going to need for each trial. You're doing each trial 3 times and you're taking the average of that. In part C, I want you to record the total number of drops used, because as we came to conclusion together, your buffered solution is going to need a lot more HCl to see a color change than your unbuffered solution. That number of drops could actually be maybe 100 drops. So you're sitting there with your lab partner, mixing your flask as someone else is dropping the acid until you match the color of your unbuffered solution with your buffered solution. Again, you will need to do calculations in this lab, so please review practice problem 12.31 from lecture 16 and also the practice problems that I went through in this pre-lab lecture.